Good morning, sir. My name is Anshul Kiawat, and me and my team will be presenting the topic of Google File Systems. Next slide. So, Google File System was designed and implemented by Google to meet the rapidly growing demands of Google's data processing needs. We have we have tried to design a mini Google File system with 5 file servers and 2 clients and a metadata server to emulate a distributed file system. To emulate this distributed file system and set of clients accessing the files, we use threading and socket programming. Now, the socket programming helps us with connecting two nodes on a network to communicate with each other, like for example, the server and the clients. And the thread is being used for multiple process for idea of parallelism using multiple threads, and since they are lightweight processes and can run a path execution within a process. Next slide. Now the GFS was designed for high fault tolerance, that is the ability of a system to operate without interruption when one or more of its servers fail. If for availability, each chunk is replicated at least 3 places and can tolerate at least 2 data or server crashes for a single chunk of data. It also has fast recovery capabilities, that is few seconds. This reduces the time for which the data is unavailable. GFS achieves high availability, high performance and implementation. It demonstrates how to support large-scale processing workloads on commodity hardware designed to tolerate frequent component failures, optimized for huge files that are mostly appended and read. We have tried to implement some of these features in the mini version of GFS, which would be described in the implementation. Now I would like to call Ashish for further explanations. Ashish.
Hello, sir. My name is Ashish, and I'm going to talk about this unique client-server architecture of the Google File System. So, this client-server architecture is unique in a way that there is a master server, and there are various mini server which is managed by this master server. So, what does this structure look like basically? So, there are small chunk servers which are basically of size 64 MB and is managed by a master server that contains the metadata, that contains information of what files or what part of files are stored in these chunks, so that when client will when want to read the file or want use of that file, it will first access the master server, and then it will send the data to the client, and it will then access the chunk server. Next slide. So you can see here, this is the GFS master which contains the chunk data, which is of here at the top you see /4/var, which is the metadata, the information of the chunk, that all metadata is holded by the Google File System master. The client first contacts the Google File Systems master for the chunks information to access the file, and then from here on it starts accessing the file from the chunk server directly. Next slide. So the problem was storing the large files. That how large file will be stored in this way, in this architecture, how large file will be managed. So first the large file is divided into the chunks, and a total of 3 replicas of each chunk is stored on the different chunk server. Different chunks, it is stored on different chunk server for a sense that if one of the server fails and that file is still is required by a client, then the data won't be lost. So also to ensure that how when a server is alive or not, a heartbeat message is sent by the master to ensure the working of the server, and a total replica count of 3 is maintained in a way that if the server dies, if a server failure occurs, then the files on that server is now copied by this master to maintain the replica count of 3. Next slide. So we have been talking about now metadata. So what this metadata actually look like. So we have a file, and like here you see a file name, and it has several chunks which is stored in different locations, and the different replicas is stored in different servers. This all metadata is contained in the master server. Next slide. So now we're going to talk about the client server interaction. So as I told that client will first interact with the master server for the metadata of that specific chunk server where data is stored. So what the master will do is that it will send the 64-bit ID or handle of the chunk server to the client, and which will be stored in the cache by the client for further accessing of the chunk and the file stored in that chunk server. So this way we can see that how it handles lots and lots of people and lots of servers and manages in a very smooth fashion. Like first it will contact with the master, and the now load or burden on the master is reduced, and now chunk servers will directly be contacted. Okay, so now I'll pass to Parth, who will explain more about the master node. Parth.
Hi sir, I am Parth, and my responsibility in this project to develop the master node. GFS cluster contains the primary server and several chunk server which are accessed by multiple clients. The master server manages all the metadata of file system, including namespaces, access control, mapping of files to chunks, physical location of chunks, and other relevant information. The master server acts as a coordinator for the cluster. The master server also keeps track of metadata, which is the information that describe the chunks. Next slide. So the GFS separates the replicas into two categories. One is primary and second is secondary replicas. So primary replica is the chunk that chunk server sends to the client, and the secondary replica serve as a backup on the other chunk server. The master server decides which chunk will act as a primary or secondary. If the client makes changes to the data in the chunk, then the master server let the chunk servers makes the changes to the data in the chunk. Then the master server let the chunk server with secondary replicas know that they have to copy the new chunks off to the primary chunk server to stay current. Next slide. Now, what actually master operations are? Let's discuss it. So, first is namespace management and locking. Locks over region of the namespace to ensure proper serialization and allow multiple operations at a time. Second is replica placement. Maximize the data reliability and availability, and maximize the network bandwidth utilization to exploit the aggregate rate bandwidth of multiple racks. Third one is garbage collection. GFS doesn't immediately reclaim the available physical storage file when the file is detected. Last is the stale replication detection. So there is one problem in this one, or we can say this method, that chunk replica may become stale if chunk server fails or misses the mutation. So what is the solution? The solution find that for each chunk, master maintains a chunk version number. Next slide. Now there is a last master operation. What is that? Creation, replication, and rebalancing. So chunk replicas created for three reasons: chunk creation, chunk replication, and chunk rebalancing. So let's discuss about the creation. Master considers several factors like place new replicas on chunk server with below average disk space filterizer, limit the number of recent creation on each chunk server, spread the replicas of chunk across racks. Now let's discuss about the re-replication. Master re-replicate a chunks as soon as the number of available replicas fall below a user-specific goal. When a chunk server becomes unavailable, when a chunk server report a corrupted chunk, and when replication goal is increased. Now let's go rebalancing. Master rebalance the replicas periodically for better disk space and load balancing. Next slide. So that was the theory part. Now let's move to the implementation of master node. These are the some code snippets of function which are written by me for master node. Next slide. And these are the some code snippets of function which are written for messaging, like heartbeat message and meta message, which are generated by master node. So this was my part. Thank you. Now Shivam Tyagi will take over.
Thank you, Parth. Next slide. Now, I, Shivam Tyagi, I am here to discuss about the chunk size. Chunk size is one of the key design parameters. We have chosen 64 MB, which is much larger than the typical file system block sizes. Each chunk replica is stored as a plain Linux file on a chunk server and is extended only as needed. Next slide. Next slide. A large chunk size offers several important advantages. First, it reduces the client's need to interact with the master because read and writes on the same chunk require only the one initial request to the master for chunk location information. This, this reduction is especially significant for our workloads. The second is this, since on a large chunk, a client is more likely to perform many operations on a given chunk. It can reduce the network overload by keeping a persistent TCP connection to the chunk server over an extended period of time. Third one, it reduces the size of the metadata stored on the master. This allows us to keep the metadata in memory, which in turn brings other advantages. Next slide. Now, on the other hand, a large chunk size, even with lazy space allocation, has its disadvantages. A small file consists of a small number of chunks, perhaps one. The chunk servers storing those chunks may become hotspots if there are many clients are accessing the same file. Now, few chunk servers storing this executable were overloaded by hundreds of simultaneous requests. Now, the solution of this disadvantage is to allow the clients to read data from other clients in such situations. Now, from here, Ujjwal will handle.
Hello everyone, myself Ujjwal. In this section, we will talk about fault tolerance and diagnosis. The greatest challenges in designing the system is dealing with frequent component failures. The quality and quantity of components together make these problems more, as we cannot completely trust the machines, nor can we completely trust the disk. So here we discuss how we meet these challenges and the tools we have built into the system to diagnose problems when they inevitably occur. Next slide. Among hundreds of servers in a GFS cluster, some are bound to be unavailable at any given time. So we keep the overall system highly available with two simple yet effective strategies, that is fast recovery and replication. Next slide. So first we will discuss fast recovery. Both the master and the chunk server are designed to restore their state and start in seconds, no matter how they terminated. Clients and other servers experience a minor hiccup as they time out on their outstanding request. They reconnect to the restarted server and retry. Next slide. In replication, we will consider two things. First is chunk replication. The master clones existing replicas are needed to keep each chunk fully replicated as chunk servers go offline or detect corrupted replicas through checksum verification. Although replication has served us well, we are exploring other forms of cross-server redundancy such as parity or erasure codes for our increasing read-only storage requirements. And in master replication, the master state is replicated for reliability. Its operation log and checkpoints are replicated on multiple machines. So for simplicity, one master process remains in charge of all mutations as well as background activities such as garbage collection that change the system internally. Next slide. Data integrity. Each chunk server uses checksumming to detect corruption of stored data. Given that a GFS cluster often has thousands of disks on hundreds of machines, it regularly experiences disk failures that cause data corruption or loss loss on both the read and write parts. We can recover from corruption using other chunk replicas, but it would be impractical to detect corruption by comparing replicas across chunk servers. So that therefore each chunk server must independently verify the integrity of its own copy by maintaining checksums. On the other hand, checksumming has little effect on read performance for several reasons. Since most of our reads span at least a few blocks, we need to read and checksum only a relatively small amount of extra data for verification. Next slide. Diagnostic tools. Extensive and detailed diagnostic logging has helped immeasurably in problem isolation, debugging, and performance analysis, while incurring only a minimal cost. Without logs, it is very hard to understand transient, non-repeatable interaction between machines. GFS servers generate diagnostic logs that record many significant events, such as chunk servers going up and down. These diagnostic logs can be freely deleted without affecting the correctness of the system. However, we try to keep these logs around as far as space permits. So from here on, Naman will take over.
Thank you, Ujjwal. Hello, sir. Myself, Naman. I will explain the functionality of our mini Google file system. So, the image shown here represents how a Google file system works with master client chunk server and uh, the client server. So, we tried a distributed system with file servers, three clients, and a metadata server to emulate a Google file system. The file system required to emulate has one directory and number of text files in that directory. A file in this file system can be of any size. However, a file is logically divided into chunks. So our chunk size is kept as 8 bytes in our implementation. All the chunks of a given file need not be on the same server. So the M server, as told by Parth, maintains the following metadata about files: file name, names of files that correspond to chunks of the file, which server holds which chunks, and at last, which was a chunk to server mapping last updated. So initially, the M server does not have the chunk name to server mapping, nor does it have the corresponding time of last mapping update. Every 5 seconds, the server and send heartbeat messages to the M server with the list of files they store. The M server uses these heartbeat messages to update the metadata. If the M server does not receive a heartbeat message from a server for 15 seconds, the M server assumes that a server is down and none of its chunk is available. So this is a small code snippet showing how multiple threads are being created to run all the three clients, 5 servers, and a meta server. We can also run all these in different terminals to observe the behavior of each node separately, but to make the presentation not bulky, we are going to run all these in a single terminal using threads. As you can see, there are 5 servers created with the ID of 1, 2, 3, 4, 5, and 3 clients are created with ID of 6, 7, and 8, and a meta server is there with an ID of 9. So this is a sample output when we run our code, how it will show. So I will show you this in practical. Let me share my screen. So this is our entire code base. The source folder contains all the code part, which have 4 folders respectively. This is the algo part containing some of the algorithms needed, and these are the files that represent the model of each message type, from heartbeat message, commit message, and other message type. This is a node part where we have written each node's code in a separate file called so here you can see meta server, client server, and normal server, and these are node listener and node.java are the basic files of each node. And this utility class holds all the important functions that a node can perform irrespective of its designation, either either it is client or server. These files 1, files 2, file 3, files 4, 5, these 5 folders represent the database of each server. In our case, there are 5 servers, so these are file folders, and these will store the chunks that will be made. And the file info.txt file will store the metadata of the M server. So let me run the code. So as soon as we run this, so as you can see, the clients and receiver. Hold that. So in the start, these 5 servers, 2, 3, 4, these all 5 servers have been started, and now they are waiting for other clients and nodes to be started. As soon as these nodes start, the files are being sent and received between each client, like 7 and 8 have sent and received each other's messages. So send each other some messages, and at last, when everything is sent and all, then the code has stopped. Okay. So after as I've run this code, I will show you how these so these are the folders just created right now after we have run the code, and each server when the file is divided and the metadata has been stored in file info.txt in this form. Okay. So the clients wishing to create a file, read or append to a file in your file system and send their request to the M server. If a new file is to be created, the M server randomly asks one of the servers to create the first chunk of the file and adds an entry for that file in the directory. For read and append operations based on the file name and the offset, the M server determines the chunk and the offset within that chunk where the operation has to be performed and sends the information to the client. Then the client directly contacts the corresponding server and performs the operation. So at last, in effect, clients and servers have successfully communicated with each other to exchange data, while the clients and servers communicated communicate with the M servers to exchange metadata. So that's it. That's all from our side. Thank you, sir.